Bismillahirrahmanirrahim. Now, inshallah, we shall talk about the converse of the angle bisector theorem. Now, if you recall, the angle bisector theorem stated that if a point is on the angle bisector of an angle, then it is equidistant from the sides of the angle. So the converse of the angle bisector theorem is going to state with that if a point is equidistant from the sides, then it lies on the angle bisector. So let me write that for you. Like thus. So if a point is equidistant, that is D is equidistant, for example, from the sides AC and AB, so which means DF is congruent to DE. That's what that means. So it's equidistant. And you measure distances obviously perpendicular. So you would measure distance like over here or something like that. So the perpendicular distance is measured, of course, as you know. So DF is congruent to DE. Okay, that's given information. The point is equidistant. Then it lies on the angle bisector. That is, if you shoot an array from here, from the vertex A, that's the angle bisector. It means these two angles are congruent. Okay, then it would hit D like the target, so to speak. would go straight through D. Right, so that's what the converse of the angle bisector theorem states. Now, how do you go about proving this? Okay, the analogy is also very similar to what we did for the perpendicular bisector theorem converse. That is, what we did a one up. We did even better than that. We said D lies on the perpendicular bisector. Darn it, because D is actually makes the perpendicular bisector. It makes the perpendicular, or it can make the perpendicular bisector. So we make the angle bisector. So what we're going to prove that is this ray AD over here, okay, or segment AD, is going to be the angle bisector. Okay, so we're going to prove AD is going to make these two angles congruent. That's what we're going to do. So that's our modus operandum. That's kind of like a thought process as how we're going to prove this. Okay. Now, again, I'm going to kind of outline the proof for you and kind of leave the proof for you. So what we're going to do is we're going to construct this segment. So we're going to construct the segment. Okay. So the given information would be here, as I've drawn on this little diagram here. The given information would be that DF is going to be congruent to DE over here, or DE is going to be congruent to DF. And that's all that would be given. And then we would have to prove that D lies on the perpendicular bisector. So what you do is you construct this segment over here, AD. Once you construct that segment, the idea then is to prove that these two triangles are going to be congruent. And once you prove those two triangles congruent, then you can use, what else you're going to use, right? You're going to use CPCTC to prove that those two angles that D is going to create are going to be congruent. And once you've proven those two angles are congruent by CPCTC, right here, then you can say that AD is the angle bisector, and since D is on the angle, therefore D is on the angle bisector of that angle. So the question then becomes, how do we go about proving that those two triangles are congruent? So we're going to construct those two triangles. Now we have this given to us, right? And then that's the perpendicular distance here, right? Okay, so that we know that those two angles have to be congruent, because that's how you measure distances between a point and a line, a perpendicular distance. So we know that that's a right angle, that's a right angle, and all right angles are congruent. And we know those two distances are these two segments are congruent, and that's given. Now we also know that is a shared side between those two triangles because of reflexive property. And these two triangles can be proven congruent by this time hypotenuse leg, because the hypotenuse is common to both of them, and the leg is the DE and DF. So we can use hypotenuse leg in this case to prove the two triangles congruent, and then finally these two angles would be congruent by CPCTC. So here's the outline of the proof. We construct AD, segment AD, and after we construct AD, then we can state that DE is congruent to DF, and this is the given information. And we also know that angle DEB, that's this angle over here, or DEA, we can use DEA, is and angle DFA are right angles, and then we can say these are congruent. Angle DEA is congruent to angle DFA because they're right angles, and then we can say that AD is congruent to AD since time immemorial because of the reflexive property. And then we use hypotenuse leg, and from there we use CP, CTC. Corresponding parts of congruent triangles are congruent. Then we say that AD, okay, bisects, okay, angle BAF, okay, or BAC. That was the original angle, BAC, and therefore, since it bisects it, it is the angle bisector. CA, since D is on the angle bisector because it makes the angle bisector. Okay, so that's the thought process behind the converse of the angle bisector. So these are two theorems with their converse, the perpendicular bisector theorem and the angle bisector theorem. These theorems we're going to need to learn some of the most exciting theorems coming up in all of geometry next time. Until then, as-salatu was-salamu ala rasulillah walhamdulillahi rabbil alameen. Assalamu alaikum.